All right, so we're going to continue looking at section 8.5. Okay, it's in your book. If you're using the packet, it's still section 5.4. All right, so yesterday we did a lot of work with vectors visually, which is really good if you're doing a word problem to make a diagram. But if you're just doing a problem and you want to add vectors or scale them, it's a lot easier to work with numbers. Okay, so we'll be talking about a new notation we can use today called unit vector notation. And that's going to be the notation we stick with for pretty much the rest of the unit on vectors. All right, so first thing they mention in this section is what it means for two vectors to be equal, just looking at the algebraic notation. Okay, what does it mean for the vectors to be equal visually? Aiden?
They have the same length and same direction.
They have the same magnitude and the same direction. Yep, same length, same direction. It doesn't mean they're drawn in the same spot. That's okay. But they have to have the same length and same direction. Well, if we're thinking about it in this notation, it means that the horizontal components are equal and the vertical components are equal. All right, so this kind of takes some of the visual part away from it. Just make sure x1 and x2 are the same and y1 and y2 are the same. Okay, any questions on what it means in algebraic notation for two vectors to be equal? Okay, and for our purposes, anytime you see a letter that's a vector, if you want to put an arrow over it, you can. I'm just going to pretend all these letters are bold letters. Okay. All right, so let's take a look at that other notation we can use to write vectors. Okay, it's called unit vector notation. When we get into 3D, it's the way we're going to do 3D vectors as well. But first, what is a unit vector? We mentioned that yesterday. Brian?
It's basically a vector that's unit is with basically one.
Okay, what's one? The what?
The length of the magnitude.
The magnitude of the length. Yep. All right. So when we write things in unit vector notation, we're basically going to use two special unit vectors. Okay. And the two unit vectors that we're going to use are called I and J. Okay. I is a unit vector that points one unit to the right. Okay. J is a unit vector, again, 1 unit long, and it points up. And basically what we can do is we can stack together i's and j's, as many as we need, to kind of build any vector we want. Okay, so think of i's and j's as like building blocks. You just stack them together to build vectors. All right, let's see how that worked. Okay, on the right side I have a picture of I and j. Okay, I is a unit vector. It's 1 unit long, points to the right. Okay. J is a unit vector. It's 1 unit long, and it points up. Okay, so any questions on what I and j are? All right. So what I'm going to try to do is I want to build the vector 3, 4 using i's and j's, and I think that'll tell you how to write this vector in a new way. All right, so let's look at that. All right, so in that vector, what's my horizontal component? The 3. And what about my vertical component? The 4. Okay. What I'm going to do, when you start stacking these together, especially if it's on axes that are the same color as your arrows, they can be a little hard to see. So let's try that. All right, so the horizontal vector, what did we call that one? Is that I or is that J? I. Okay, so this is I. And how many i's am I going to need?
Right.
Yeah, I'm going to stack 3 of these together. Okay, so there's 1, there's 2, and 3. Okay, so I have I plus I plus I. Okay, each one of them is 1 unit long. So together I have something that's 3 units long, and that's the horizontal component, 3. Okay, now how many j's do I need on the end of that? 4. Okay, so just make our copies. And we're just going to put our j's. 2, 3, and 4. Okay, so now I've stacked together 4 j's. And if I connect where I started to where I finished, that's the vector 3, 4. But how do you think we could write it in our new notation? How many i's? 3 of the i's. How many j's? 4 j's. And what did we do with all the i's and j's? Visually, I just did it. I added them all up. Okay, so 3i plus 4j, that's the unit vector way to write 3, 4. It's pretty simple. Okay. When we go through problems, we'll do a mixture of the algebraic notation and unit vector notation. Okay, you need to know both.
What's the point in converting?
When we start to do other operations with vectors, especially in 3D, you'll see how we can set this up, especially in like a matrix. But really, you don't have to convert. You can do it either way. Both ways are pretty straightforward. Yeah. I'd say most people do use unit vector notation rather than the brackets. Just the way they do it. All right, so let's look at some formulas for vectors. We did a lot of this yesterday visually. Now we're just going to look at it using formulas. Okay, so I've got 2 vectors, v and w. Okay, v I've written in algebraic notation, and w I've also written that way. We could do it with unit vector notation if you wanted. It would be x1 I plus y1 j. Okay, whatever x1 and y1 are. This would be x2 I, y2 j. Okay, how do you think we would do v plus w? And you could just give it to me with the algebraic notation. Aiden?
X1 plus x2, comma, y1, or x2 minus x1, comma, y2 minus, no, yeah, so x1 plus x2, comma, in parentheses, comma, y1 plus y2 parentheses.
Yeah, just combine your horizontal components by adding them, and then combine your vertical components by adding. Okay, if you were going to do this in the unit vector notation, it would be like x1 plus x2 in parentheses with an I on the outside, plus y1 plus y2 in parentheses with a j on the outside. Okay, how about subtraction? What's the only thing that would change? Yeah, the plus turns into a minus. Okay, what's nice about doing it subtraction this way compared to how we did subtraction of vectors yesterday? Yeah?
I have a question. I thought the terminal one was the one that you're supposed to be having the things subtracted from.
That's when we had coordinates. Yeah. So now we have actual vectors. Yeah. So, anybody tell me why, or what's different about subtracting the way we are today versus the way we did yesterday? Yep.
Isn't it because it's 1 minus 2 and 1 minus 2 compared to it being 2 minus 1?
Well, that's what Kanan said. We're mixing
I was
ideas
asking
there.
if that was the reason.
No. that had to do with finding a position vector given an initial and terminal point. So that's a little different. How did we subtract vectors yesterday? Or how did we add vectors yesterday? Graphically, right? So when we subtracted vectors, we had to flip W around, right? Find the opposite of it. And then we had to connect things, the beginning of one to the end of the other. Well, this time we're not doing that, okay? We're just looking at numbers. So you don't have to do anything visual. Okay, how about scaling a vector? How do you think you would scale vector v by alpha? What, Nick? How do you think you would scale vector v?
Would it be alpha x1, alpha y1?
Yeah, you just multiply each component by the whatever you're scaling by. So in this case, it's just alpha. So alpha x1 comma alpha y1. Okay, and this symbol, what does that mean? Magnitude. All right. Any thoughts on how we find the magnitude of a vector? This is something, if you don't know, a picture really helps. Yeah?
Would be x1 squared, square of x1 squared plus y1 squared.
That's part of it, x1 squared plus y1 squared. And one more thing. Take the square root of that.
So the square root is
Oh, I didn't hear you say square root. Sorry. So now what are you really doing there? What is that? Yeah, it's the Pythagorean theorem. Okay, so if you had a vector, okay, and make a triangle out of it. Let's say this side had a length of x1. That's the vertical component is y1. Just take x1 squared plus y1 squared. Add them up and take the square root. Okay, so we'll go through an example of doing some of these, but we're not going to do adding and subtracting visually. Okay, we'll just try the formulas. Right, so I've given you two vectors, v and w, both in unit vector form and algebraic, and we'll write the answers in both ways. Okay, anyone think they could tell me using those formulas what v plus w would be? Oh, Maddie, could you tell me what I would get if I do v plus w?
2 plus 3. I don't know.
All right, so you want to combine your horizontal components. So that was good. So what would your I component be?
What?
What you just said.
Wait, I don't know what you're asking.
I want to add vector v to vector w.
Plus 3 and
Yep, and then what letter would be next to that?
I.
Yep, so that's your first part. So if we combine those, we have 5i, so that's good. And how about my j part?
-1j.
Yeah, we have a positive 3, take away 4. And you can put -1j, that's fine, or you could just put -j. That's it. 5i minus j. Now, if we were going to write it the way we learned yesterday, how would I write 5i minus j? 5 comma -1. Okay, both ways are correct. We just have to see what way they're looking for. Okay, v minus w. David, could you tell me what v minus w would be?
The answer of
Yeah.
-1 and 7.
Right, and can you write it in unit vector for me first, and then I'll write it the way you just said?
So -1i
Mm-hmm.
plus 7j.
Perfect. So negative 1i plus 7j. Or the way he said the first time, negative 1, 7. Any questions on that one? All right, so that's subtracting. Scaling, okay, we're going to triple vector v. Okay, Dominic, what would I get if I triple vector b?
6i plus 9j.
Yep, 6i plus 9j. And if we write it in the algebraic vector form, 6 comma 9. Okay, notice these last two, you don't need two vectors to perform the operation. Okay, addition is binary, subtraction is binary, meaning two. You need two vectors to do it, but you don't need two vectors to do a scalar product. You just need one. Okay, same with magnitude. Okay, so, Ashley, what's going to be my formula to find the magnitude of v?
2 squared, 2i squared,
Just the component, just the two.
just the 2, plus 3 squared.
So 2 squared plus 3 squared. And if we add those up and it's something that reduces, we should reduce it. What does it add up to?
Square root of 13.
Square root of 13. And we can't reduce that. Okay. Questions on adding, subtracting, scaling, or finding magnitude? Okay. What's the difference between A, B, C, and then D? A, B, and C have something in common, and D is a little different.
It doesn't have a unit
It's not a vector.
D is not a vector. A, B, and C, those answers are all vectors. D is just a number. Okay? All right, so just as a reminder, we mentioned this yesterday and we've already talked a little about it today. If the magnitude of a vector is 1, then it's a unit vector. Okay, what I'm going to try to do here is take vectors that are already pointing in a certain direction, and if they're not 1 unit long, I want to change it so that they are. Okay, what are we really doing to the vector if we turn the black one into the red one? We're what?
Scaling it down.
Yeah, we're scaling it down. Okay, or if we had a vector that was too small, we might have to scale it up to make it 1 unit long. Okay, but does scaling by a positive number ever change direction?
No.
No. So really, all we have to do is scale a vector by a positive number to make it 1 unit long. All right. So to find a unit vector, if you're given a vector, we're going to find a new vector. It has to point exactly in the same direction, but we have to force it to only be 1 unit long. Okay, so all we're really doing is scaling the vector. And to figure out the formula, okay, for how we do it, let's just look at a couple examples. Let's say that black vector was 5 units long. What would you have to scale it by to make it 1 unit long? 1/5. Okay, if you had a vector 5 units long and you scaled it by 1/5, it'd become 1 unit. Okay. What about if you had a vector 8 units long?
1/8.
You'd scale it by 1/8. Right, so let's write down a couple of these. Let me make up a vector that's 5 units long. 3, 4. Okay, if you use the Pythagorean theorem, it'll come out 5 units long. So you'd have to scale this by 1/5. So really what you're doing is taking 3 divided by 5 and 4 divided by 5. This vector and this vector have the exact same direction. This one has just been scaled down. So what do we scale the vector by in general?
The reciprocal of the length of the magnitude.
Yeah, the reciprocal, or 1 over the magnitude. Okay, so that's why the magnitude is in the bottom. Okay, to find a unit vector, take your vector and divide by its magnitude. That's exactly what I did with the vector 3, 4. Took that vector, divided each component by its magnitude, which was 5. And now if you did this out with the Pythagorean theorem, 3/5 squared plus 4/5 squared, that's 9/25 plus 16/25. And 9 plus 16 is 25/25. That's 1. And the square root is 1. Right? So that's the formula to take a vector and scale it to make it a unit vector. Okay? If they give you a vector and it's already a unit vector, then there's nothing to do. Right, so this problem is actually very similar to the one I used as an example. Okay, you've got the vector 3i minus 4j. Okay, let's find the magnitude of it. Okay, what's the first component that I'm going to square? And the second component? -4. That's going to give me 9 plus 16, which gives me the square root of 25, or 5. The negative has no effect compared to the problem I showed you as an example. If you've got a 3 and a 4, the length is always 5. All right, so what would be my new vector following that formula? 3/5 I minus 4/5 j. So you just take the vector and divide each component by its magnitude, which, as Aidan said, is like scaling by the reciprocal. It's like multiplying by 1 over the magnitude. Okay, if you were going to write it in the other form, it would just be 3/5 comma -4/5. Okay, any questions on that? All right, so that's finding a unit vector. All right, so 2 applications we're going to look at. The first one is a velocity vector, okay, which can model the speed and the direction of any object that's moving. Okay, today we're going to specifically look at throwing an object, and the way we'll describe it is we're going to be releasing that object at a certain angle, okay, from the horizon. So if this is your ground, let's say right here, that's the angle that you're throwing the object at. Okay, it's the angle to the horizontal. Okay, and the other thing that they'll tell you is how fast the object was going when you released it from your hand. All right. So first thing let's do is see if we can figure out our formula for a velocity vector. Right, so here's a vector representing the, bless you, okay, the velocity. Okay, for our purpose, we can pretend that this is like the millisecond it leaves your hand. Okay, basically at that point it's traveling in a straight line. Technically, gravity is going to cause it to travel more in a curved path, but this is going to work fine. All right, what shape could we make out of this? Yeah, let's make a triangle out of it. And what we're basically going to do is break this triangle up into components, or break the vector up into components. Okay. The object is traveling in what 2 directions in this problem? Up and right. Okay, so here's the up component, and here is the right component. And together, if you add up the blue and the green vector, you get the one in black. All right. Let's see which letter they use for the angle. All right, we're going to use alpha for our angle. So what trig function could I use that would involve, let's say, the blue vector? All right, cosine. And I also want to involve the hypotenuse, yeah, which is cosine. Okay, for now, we can call this x and we can call this y, but I'm going to cross that out because I'm going to know what x is in a second. All right, so we would use cosine of what? Alpha equals, yep, x over, we have to be careful what we put in the bottom here.
The magnitude of it?
The magnitude of the vector, okay? The vector itself describes both magnitude and direction. All I care about is the length of the hypotenuse, which technically is this. Okay. Now we'll get x by itself, and we'll have a formula for the horizontal component. Yeah. It's the magnitude of your vector. In other words, how fast you throw the object times the cosine of the angle you release the object at. Okay, so that's x. And remember, we have to add onto that the vertical component. Okay, so let's find that one. Which trig function would I use for y? It's pretty much the same thing. Opposite over magnitude of the vector. So what does y equal? Magnitude of the vector sine alpha. Right, now let's just take x plus y, okay, and add them up. So we've got magnitude. Actually, there's two ways we could do it. If you want to write it as an algebraic vector, this is how you could do it. Your horizontal component is magnitude of the vector cosine alpha. And the vertical component is magnitude of the vector sine alpha. But I think we're going to stick with the ij notation for this one. All right. So we have magnitude of the vector cosine alpha. And which component is that? That's the I. Plus magnitude of the vector sine alpha, and that's the j. Now, what do both of these terms have in common? Yeah, the magnitude of the vector. So what we can do is pull the magnitude out from both of them, and what we end up with is the magnitude comes out in front. We have magnitude v, then in parentheses cosine alpha I plus sine alpha j. Okay, where we need to know these two things. Alpha is the angle you're throwing the object at from the horizon, and magnitude v is the initial velocity you throw the object at.
I was going to say about like for how you're writing it, you may want to put a parentheses around the alphas to make sure that it doesn't look like the I and J are within the sine or cosine.
Yeah, if you want to put parentheses around
Just
alpha.
so it's more clear.
Yep. Again, the I is not part of the cosine function. Neither in the J is not part of the sine function. Yep. Okay, so that's your formula for a velocity vector. Okay, given an initial speed and an angle you're throwing the object at. Okay, questions on that? All right, so let's take a look at an example. Okay, this one's pretty straightforward because you have a formula. All you really have to do is plug in two numbers, and that's it. Okay, there's not really much of a diagram you need to draw. We already did the diagram, and it's really the same setup in every problem. So we just use the formula. All Right, so we're throwing an object at 50 miles per hour at an angle of 30 degrees. I want to find the velocity vector. Specifically, I want to write it in unit vector form. And I want to explain the meaning of each component. Okay, in the real world meaning, okay, when we do it out. Okay, so bless you. Okay, what's the magnitude of my vector? 50. And the angle that I'm throwing it at? 30. Right, so plugging that in, somebody tell me what my formula for my velocity vector is going to look like.
50.
Cosine 30.
Cosine 30 times cosine 32.
Oops, cosine 30
Uh,
I plus
so sine 30.
sine 30j. All right, now that's not unit vector form because we haven't done out the arithmetic. What do I need to do first here?
Distribute.
Yeah, distribute that out. And multiply 50 times the cosine of 30. All right, so
It's
so that's 0.866. In this case, I don't care about the exact answer, but what would that number be? Yes, square root 3 over 2 times 50. 43.30i. Okay, and the sine of 30 is how much? 1/2 times 50. 25. There is your velocity vector, the way that they asked for it, unit vector form. And what's the meaning of each number here in this problem? Like,
Horizontal and vertical speed.
yeah, this is basically your horizontal speed. And the 25j is your vertical speed. So knowing these two speeds, we could find out all kinds of things. What speed would I want to use to determine how long the object is going to be in the air? The vertical speed. Okay. Using this speed and knowing the acceleration, or if you're throwing an object up, I guess it's the deceleration first. You could figure out how long the object is in the air for. Okay. Objects decelerate, was it 9.8 meters per second squared? We don't have meters in this problem. I think we had miles per hour. So you'd have to convert some units. But using the vertical speed, you can figure out how long the object is in the air for. And if you know how long the object is in the air for, and you know how fast it's going horizontally, what could you find from there? Yeah, you can find out how far the object is going to go. Right? Horizontal speed, we assume, is a constant. Right? Air would slow it down, but we would assume that if you release the ball at 43.3 miles per hour horizontally, it'll still be traveling that fast when it reaches its target. Again, air resistance would be the only thing that affects horizontal speed. Vertical speed is constantly changing. Okay, the second you release an object, it's slowing down until it reaches 0, and then it starts to accelerate when it falls back down. All right, so we're not going to get into too many other, those are called kinematic problems, Newtonian kinematics, but you could figure out how high it's going to go, how far it's going to go, all kinds of basic things. Okay, questions on that? All right, so last example. This one is on static equilibrium. Right, so static equilibrium, if you kind of break the word apart and look at it, static means it's not moving, and equilibrium means that the sum of all the forces on it are balanced. Okay, the sum of all forces on it is 0. Right, and the approach, the kind of problem we're going to look at is you're going to have an object suspended from a ceiling, with 2 different length cables. And I want to find the tension in each cable. Okay, so that black line at the top, that bold line, represents our ceiling. Okay, the 2 lines coming down, those are our cables. And we have a weight of 1,200 pounds. Okay, any questions on the setup of the diagram itself? All right, so before we even sketch, anything on this picture, let's just first label what it means that this situation is static equilibrium. It means the sum of all the forces acting on it is 0. Okay? And I want you to think 2-dimensionally. Okay? So what does that mean if the forces are balanced? What forces are balanced? What are the forces that are acting on this? Mm-hmm.
12,000 pounds downward.
Yep, so you have a force down.
And then
Okay, let's call that force down.
a reaction force will pull up.
It has to equal the force pulling up, okay, which there's actually multiple forces pulling up. But in general, if the object is not moving, then that is true. Okay, what else is true? One more equation we need, or one more idea we need to think about. Those aren't the only forces in this problem. Yeah?
The cable's pulling on the ceiling.
Okay, so you could think of it as the cable's pulling on the ceiling. Let's think of it as the cable pulling on the box. But it's the same idea. What direction or directions does the cables pull?
Left, right.
Yeah, the cables are not only pulling up, but they're also pulling horizontally. Okay, think what would happen if you cut one of these cables. It wouldn't just fall straight down. It would swing in a certain direction. Okay, if you cut the cable on the left, it would swing to the right. So this cable must be pulling left. So force left has to equal the force pulling right. So that's basically what we have to set up. 2 equations, and we have to figure out the force down, the force up, the force left, and the force right. Force down, we know. Okay, that's the only thing we're going to have a number for. Everything else is going to have sines and cosines. Okay, so the next thing I want to do in the diagram is try to break the force of this cable into 2 directions. Which direction did we say this cable is pulling? The one on the left? Well, the cable's not pulling down. The weight is pulling down.
Pull up.
The cable is holding it up. So the cable's pulling up and left. Okay, so let me... So that's the horizontal component. It's pulling left. There's the vertical component pulling up. Okay, we're going to do the same thing on the other side. Horizontal component pulling right, and vertical component pulling up. Okay, because these cables are not only pulling the object up, but they're also pulling against each other, there can be more tension in these cables than there is weight hanging from it. Does that make sense? Okay, because the cables, think about a tug of war. Vertically, there's no weight hanging from the cable, really. It's just all horizontal tension. Well, there's vertical tension in this because of the weight, and this horizontal tension, think of like these cables in a tug of war. They are pulling against each other a little bit. So don't expect the tension in cable 1 and cable 2 to add up to 1,200. All right. Let's call the tension in cable 1, let's call that one T1. Okay? That's the magnitude of the vector for the first cable. And let's call T2 the tension in cable 2. That's the magnitude of the vector for the second cable. Okay. By doing it that way, I don't have to keep writing double bars every time. Just understand T1 and T2 are tensions, the magnitudes. All right, what else can I label in this diagram for, especially for angles? Right now, the triangles I want to focus on don't have any angles except the 90s labeled. Mhm.
The angle of the triangle under 45 degrees and 45, 45.
Yep. There's several ways you can figure that out. Okay. The horizontal force and the horizontal ceiling, those are parallel lines. If you think of two parallel lines cut by a transversal, then those alternate interior angles are the same. A little geometry right there.
I like that though.
Okay. If you don't want to think of it that way, think of the angle right here as a, let's see, how can we think of it? Yeah, you've got a 90 at the bottom. Okay, together, these two angles have to add up to 90 because the angle with the ceiling is a 90. So that would have to be a 45 as well. Okay, how about this angle at the bottom? Yep. And the angle at the top? 60. Now, we don't need both of the angles in the triangle. We're going to pick one. We're going to use that as our reference point to do everything. All right, so let's pick the 30, and of course that one comes out the same. Okay, any questions on that? Last thing we need to do is we need to name the horizontal and vertical forces. So you could call it Jack, or what would be another name that might help us remember horizontal? What letter? Yeah, horizontal. Somebody said X, X1, X2, Y1, Y2. Okay, however you want to do it. Let's use X1 for horizontal. X is the horizontal. And X2. That's Y1, Y2. All right, so now let's take these two equations one step further and let's translate them all into X1s and Y1s. Okay. And 1200. Okay, what's the force acting down? 1200. What's the force acting up? Y1 and Y2 are both pulling up. Okay, what's the force pulling left? X1. And what's the force pulling right? X2. All right, so now we've got our equations set up with X's and Y's, but now we need to change these X's and Y's to having tension involving T1 and using this angle. Right, so now here's where the sines and the cosines come in. So we're going to come up with four formulas. One for x1, one for y1, one for x2, one for y2. Let's start with x1. Okay, using 30 as your reference angle, what trig function would involve x1 and t1?
Cosine.
Yep, cosine. So cosine 30 equals what's adjacent? X1 over T1. So what does X1 equal? T1 cosine 30. Okay, that's one of the four formulas we need. Okay, let's do Y1. What trig function would you use? Yep, sine of 30. And sine is opposite over hypotenuse. So T1 sine 30. After you start to do this, you notice a pattern. It's always the tension in the cable times cosine if it's the horizontal tension, sine if it's the vertical tension. All right, so using that idea, I think we could just kind of generalize. What do you think X2 would be?
45.
Yep. T2 cosine 45. And how about y2?
T2 sine 45.
T2 sine 45. Okay, so now we have all four formulas. We have our equations. Just fill in all four of these formulas in these four spots. And then we're going to have just algebra from there, okay, to solve the equations. So the physics part is done. The trig part is done. Now it's just going to be algebra. So we got 1200 equals y1, which is t1 sine 30, plus y2. y2, t2 sine 45. All right, next equation, x1 equals x2. t1 cosine 30 is going to equal what? T2 cosine 45. Great. What kind of problem is that? You study it in Algebra 1 with two equations with two variables. Begins with an S.
Substitution.
Well, that's a method you can use to solve it, and that is the method we're going to use here. That's a system. Okay? Two equations, two variables. It's a system. So, as Autumn said, one way to solve it is with substitution. Take one of your equations, try to take the simpler one, get a variable by itself, and then plug it back into the top one. So, which equation is smaller to work with, the top or the bottom? Bottom. And now we can solve the bottom one for either T1 or T2. T1? All right, so I'm just going to put using equation 2. Okay, so using equation 2, solve for, what did we say, which one?
T1.
T1, okay. So what will T1 equal?
T2 cosine 45 over cosine 30.
T2 cosine 45 over cosine 30. Now, what are you going to do with that? We can find some decimals eventually. We're going to have to, yeah. But not yet.
Plugging in for
Yeah. So now, plug in, I'm just going to put an arrow, plug in that in equation 1 for what letter?
T1.
T1. Okay, so now plug in that box in equation 1 for T1. All right, so what do we have? 1200 equals, it was T1, now replace T1. So T2 cosine 45 over cosine 30. And what else was next to T1 in the top equation? Sine 30. That's still there. Okay, in a minute, again, we need a decimal for that. Okay, what comes next?
It's plus T2 sine 45.
Yeah, plus T2 sine 45. Now, how many variables do we have in that problem?
One.
Too many?
No,
Just only one.
Just one. Just T2.
And one is too many.
Okay? So at this point, let's use our calculator and get some decimals, because we have to round this off. So let's find cosine 45 times sine of 30 divided by cosine 30. Okay, and you should be in degrees, so I need to fix that. Sine of 30 divided by cosine 30. Okay, Anybody get an answer for that?
0.08.
Yep, 0.408. Okay, instead of putting T2 times 0.408, we usually put the variable after. So I'm going to put the T2 after it. Plus, what's the sine of 45? 0.707. All right, what would I do now? Do what?
No, you had point.
You could factor out the T2, but I don't think you need to.
You add the 0.408 to the 0.707.
Yeah.
Because they're the
Like
same.
terms.
Yep, just combine your like terms. 0.408 plus 0.707, 1.115. So now we divide by what? 1.115. And what does that come out to?
1,076.23.
1,076 point,
23.
1,076.23, and that's tension, so that was in pounds, I think.
Yes, no.
And our last step, we have a formula for finding the tension in cable 1 from the work we already did. Now fill in T2 cosine 45 over cosine 30. What was it? T2. 0.23. What was the rest of it? Cosine 45 divided by cosine 30.
0.408.
Is it pounds?
Isn't that 0.408?
What, Brian?
Isn't that 0.408 times 1,076.23 because we already did it on top?
Oh, we already did cosine.
Yeah, we did that to get 0.408 T2.
Yeah, so if we had some arithmetic we could reuse, but that's fine. If I don't, if you don't remember what it is, we'll just type it in again. Okay, so I just filled in T2 times cosine 45 divided by cosine 30, and that'll give me T1. So do we have the tension in cable 1?
878.74.
878.74. Does that add up to 1,200 pounds? No, definitely not. And again, that's because the cables were pulling against each other. If the cables were perfectly vertical, okay, and assuming that the 1,200 pounds in a box was evenly distributed, it wasn't on one side of the box or the other, then the tension would be exactly 600 pounds in each. Once you start putting the cables at an angle, the tension goes way up. Especially if you had the cables almost like a tug of war pulling horizontally, it'd be a lot of tension. Okay. All right, so the basic steps in that problem. Set up your force up equals force down, force left equals force right. Okay. Then after you make your diagram, turn everything into sines and cosines. Okay, that's finding your components. And then the last step is to solve a system. Okay, so I don't think any one of those things individually is hard, but putting it all together, it's a lot of stuff to do in one problem. Okay. Hey, questions on static equilibrium? It's probably one of the longer applications we do this week, but we'll do another type tomorrow. There's another example they do in the book with forces. Finding a resultant force. That's kind of like if you push up and your friend pushed left, the resultant force is up and to the left. We're not going to go through resultant force. Okay. We're going to hold off on that. Okay, which means on page 344, 69 was a resultant force. And so was 64. Okay, so on page 344, just try 25 to 47 odd. 55 and 57 are both velocity vector problems, and 66 is static equilibrium. If you didn't understand the one we did in class, you could probably do 66. It's the exact same problem, except the weight is 800 pounds instead of 1,200. Okay? You can't see it in the picture because it's kind of blacked out on the copy, but if you read the word problem, it says the weight is 800 pounds. Okay, so we'll take a look at that tomorrow. That's going to finish up intro to vectors, and then tomorrow we'll look at dot product.